Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on electricity and magnetism. We have been discussing about a series of lectures on the subject electrostatics. This lecture is devoted to the topic on the dielectrics and the effect of dielectrics in capacitors. Before we start the lecture, let us see the session outline for today's lecture. In this session, we are going to see the concept of dielectrics at length. Followed by that, we are going to see the types of dielectrics and also the effect of dielectrics in capacitors under two conditions: when the charge remains constant and when the potential remains constant, and also the force between the plates of the capacitor and the effect of introducing the dielectrics there also when the charge remains constant and also the potential remains constant. So, all these topics we have in store in this lecture. Let us start with the basic definition for dielectrics. What is a dielectric material? Let us see the definition for it. A dielectric is a non-conducting material such as rubber, glass or waxed paper. When a dielectric is inserted between the plates of a capacitor, the capacitance increases. If the dielectric completely fills the space between the plates, the capacitance increases by a dimensionless factor by epsilon r, or it is denoted as K, which is called the relative permittivity or dielectric constant. The dielectric constant is a property of a material and it varies for material to another. Basically, the dielectric constant is nothing but the relative permittivity. I hope the term permittivity, the permittivity of free space and absolute permittivity of a medium and the relative permittivity of a medium, all these are familiar to us. We have already learned them under the very basic electrostatics concepts. The same relative permittivity is given a new name as far as the capacitors are concerned with the term dielectric constant. What is a dielectric material? It is basically again a non-conducting material. We know the difference between conductors, insulators or non-conductors, all that, right. So, it is the very same non-conducting material like rubber, wood, glass, mica, all that. Why they are called non-conducting? When charges are there on the non-conducting material, it cannot move on its own, it cannot move from one place to another in a non-conducting material because of the very nature. But these dielectrics behave in a slightly different manner as far as the application of electric field is concerned. In a metal or in a conductor, when electric field is applied, the electric field just passes through it, and because of the field, the charge, free charge in the conductor, that also will get affected. Positive charges move in the direction of the electric field and negative charges, mainly the electrons, move in the opposite direction. But in the case of a non-conducting material, which we call here as a dielectric material, the electric field is not just passing through it because of the nature of the material. It is getting reduced in some of the cases due to some phenomenon that is happening in the dielectric material. What are the phenomenon happening? If you want to go deeper into that, we should know by what means these materials are made. These are made with atoms or molecules which behave in a slightly different manner as far as these dielectrics are concerned. So, we have already learnt a good old concept, the dipoles, right. These materials are made up of dipoles. Either they would have permanent dipole moments, or when the electric field is applied, they get polarized, and thus the induced dipole moments are appearing in the material. We will learn more about it as we see some of the visuals related to these dielectric materials. For any given separation D, the maximum voltage that can be applied to a capacitor without causing a discharge through the dielectric medium is called dielectric strength. What is dielectric strength? The dielectric strength of the dielectric, it is nothing but how much of the maximum voltage that it can withstand. The maximum voltage that material can withstand, or it can be applied to the capacitor without causing a discharge through the dielectric medium. This is called the dielectric strength. What is the meaning of it can withstand? See, when we apply the electric field, there is a voltage developed across the 2 points, maybe the capacitor plates will have a difference in potential, and as we increase the voltage, the electric field is also likely to increase. This electric field will make the dielectric material to have the dipoles align in the direction of the electric field. At one point, at one particular voltage, these dipoles are likely to physically get separated by charges. The positive charge will start moving in the direction of electric field, negative charge will start moving in the direction opposite to that of electric field. So, there is a great breakdown likely to happen. That is called the breakdown that is happening across the two capacitor plates. So, there is a limit up to which only these dipoles also can withstand the electric field. Let us see what we have further. If the magnitude of the electric field in a dielectric exceeds the dielectric strength, then the insulating properties fail and the dielectric begins to conduct. The insulating materials have values of K greater than unity and dielectric strengths greater than that of air. We will look at the numerical values to understand the meaning of dielectric strength. What is called dielectric constant and what is called dielectric strength. We will go ahead with the numerical data. So, this table shows you the numerical values. For air, the dielectric constant is nearly equal to 1, because this is the relative permittivity. The dielectric constant, what we have noted here, could be denoted as the relative permittivity epsilon r, both are one and the same, and the related dielectric strength is also shown, and it is highlighted here. What is it? What is dielectric strength? It equals the maximum electric field that can exist in a dielectric without electrical breakdown. So, these values are shown here. The unit for that is the voltage that is applied per unit length. So, V divided by M is the unit for the dielectric strength. Maybe one or two values we can take, like nylon, the dielectric constant is 3.4 and the dielectric strength is 14 into 10 to the power 6 is the value. So, that much of voltage per meter if you apply, the material is likely to withstand up to this. Beyond that, it will have an electrical breakdown. And Teflon value is also shown here. It has got a very high dielectric constant and a relatively high dielectric strength. So, this data will help you to understand the meaning of the dielectric constant and the dielectric strength. What is the role of this dielectric in a capacitor? We know in a capacitor we have the high electric field existing between the two plates, the positive and the negative plate. When we insert this dielectric medium between the two plates, what is likely to happen? As I said, if the material has got already the permanent dipoles, they will align in the direction of the dipole moment will align in the direction of the externally applied electric field. If it is not having the permanent dipoles, then the material is likely to get polarized and thus align in the external field. That is what is likely to happen. So, we can classify the dielectrics into two types. What are the two types? Let us see. The materials which have the permanent dipoles, they are called polar molecules, right. Water is one good example. The water molecule H2O has a permanent polarization resulting from its bent geometry. The molecular arrangement itself is bent in a particular way. It is shown here in the picture. The center of the positive charge distribution is at the denoted point x. See, here it is marked as x. The hydrogen has given one electron to the oxygen and thus the two hydrogens have donated electron to the oxygen. So, it has acquired the negative charge, it has become negative, oxygen has become negative here. The hydrogen atoms are becoming positive because they have lost the electron. So, their charge center, the positive charge center is here, the negative charge center is here. So, it is separated by a distance. So, there is a permanent dipole moment. The dipole moment is from which direction to which direction? Any idea? We have learnt about the dipole moment in the earlier lectures. It is from negative to positive. So, this is the direction in which the dipole moment P exists. The direction of dipole moment is existing like this. Now, we will go ahead with the non-polar molecules. What will happen in non-polar molecules? The induced dipoles will arise. The symmetric molecules have no permanent polarization because the charges are not separated. An external field induces a polarization in the molecule. The example that we have here could be taken as the CO2 or any such molecule which has got the symmetrical arrangement. We have a negative charge here and the positive charges here and the charge centers coincide. The negative charge center is here, the positive charge center is also here. So, it is not having any dipole moment. But when the electric field is applied in this direction, this negative charge center is likely to move opposite to that of the electric field. So, there is a possibility for permanent dipole. The positive center would have moved here, the negative center would have moved to the left. So, there is a dipole moment arising, it is from negative to positive. In the earlier case, the permanent dipole is existing, there is no need for external electric field. But for the second case, there is a need for external electric field. Only in the presence of external electric field, the dipole moment is existing. See, here there is no electric field existing in this case. So, the dipole moment is not existing. So, this is how the polarization are producing the induced dipole moment in a non-polar system. Polar system they already have, non-polar system when the electric field is applied it will have. So, whatever be the case, but when we apply the electric field both for the polar system and also for the non-polar system, what is likely to happen? The alignments will happen, the dipole moment will align in the external field. Let us see one or two clippings on that. This depicts the case which I have been trying to explain. So, in the absence of the applied electric field, the dipoles are at random in a dielectric medium, maybe it is a polar medium. See, the dipoles are aligned in the random orientation, they do not have any particular alignment. In the case of non-polar molecules, even this dipole will not exist. Okay. Now, when the field is applied, it is shown here from left to right, the E0 is the applied electric field, the dipoles align under external electric field. This is how the alignment is happening. The positive charges are aligned in the direction of the field, negative charges in the opposite direction. So, the dipole moments are aligned in the direction of the external field. Though we say there is a perfect alignment happening in the presence of the external field, there will be a kind of thermal vibration always present in these materials. That thermal vibration will slightly disturb the alignment. So, that will definitely be there. In the presence of such thermal vibration, this external field is influencing the dipoles to align like this. What is the net effect of this? Forget about the alignment now. See here, the positive negative all cancel. Look at the extremes. This right hand side has the accumulation of positive charge and the negative side has got the accumulation of negative charge. So, that is only highlighted here. Right hand side you have a look at it, all the positive charges are aligned. Left hand side you see all the negative charges are all aligned. What is now happening? There is a strange thing, right? See, this is the externally applied field E0, but because of the charge separation, there is another induced electric field. It is existing from this induced positive charge to the induced negative charge, that is what is highlighted here as electric field due to the induced charges. So, have you understood this concept clearly? In the case of dielectric materials, when they are subjected to external electric field, that is existing, but because of the induced charges, there is an electric field produced in the opposite direction to that of the external field, that is called induced electric field, but it will be never equal to the applied electric field, it will be slightly less, but in some of the materials, the strange cases like metals and all that, it will be equal to that of externally applied field, but I do not want to discuss that elaborately, but let us have a look at the way in which the induced electric field is appearing. Now, what is the resultant of that? So, inside the material, the dielectric material, the electric field gets reduced by what value? Have a look at this expression. See, there are two expressions shown here. One shows there is a reduction, right. So, it shows the difference. This is the resultant electric field. This E0 is the applied from external source and E induced is due to the induction. So, there is a difference. The E seem to be reduced, it is less than that of E0, and this could be written as a ratio also. This E, if it is measured, it is reduced by a factor K. What is K here? It is the dielectric constant K or relative permittivity epsilon, or any one we can use, but invariably for all the expressions hereafter we will be using the K, dielectric constant. Because of the reduction in the electric field, the potential is also getting reduced. Now, when the external field is removed, what will happen? Once again the alignment will get disturbed. So, the material will behave as a randomly oriented dipoles. The field is not going to exist inside the material. So, the opposite field or the induced field is going to exist in the presence of the externally applied field only. When it is removed, it will also get disturbed. I mentioned about the dielectric strength, right. Now let us have a look at the visual, try to understand how the electrical breakdown is likely to happen in a dielectric material. Have a look at this visual again. Look at this. When this field is increased, it is becoming higher and higher. What will happen? There will be a breakdown happening. These dipoles will physically get damaged. The positive charge will move in the direction of the electric field. The negative ion, or how it is going to happen, all that we are not going to learn now. The negative charges will move in the opposite direction. There is a tremendous heat going to get generated because of the physical damage that is happening in the molecules. So, such a thing is called electrical breakdown in the dielectric material. So, we sometimes use the term dielectric strength. So, this how much of voltage per meter this material can withstand. So, that itself is called the dielectric strength. Have you understood it now? Now, when such a dielectric material is placed in the capacitors, what are the effects? That is what we are going to see. This is showing the effect of the dielectric that is placed in a parallel plate capacitor. We will discuss it under a condition when charge remains same, which is called an isolated capacitor. So, let us consider a capacitor which has got already charged. How do we charge it? We connect it to an external battery, a source. It acquires the charge and it is removed, detached. So, it cannot give the charge to anything else. So, that charge remains constant on the plate. To such a plate, we connect a voltmeter. It is just shown for understanding. It shows a value V naught. The C naught is the capacitance, Q naught is the charge present on it, and V naught is the potential that is measured across the two plates. So, this is the expression we have for the capacitance. C is equal to Q divided by V. So, we write it for this case, C naught is equal to Q naught divided by V naught. This is written from the very definition. Now, what do? We insert the dielectric material. When the dielectric material is introduced, what will happen? The capacitance has to increase, the potential will decrease by this factor. We have seen it in the earlier case, because the electric field decreases across this, potential decreases. So, as the potential decreases, the capacitance increases. We bring this K to the numerator here and conclude the capacitance increases when we introduce the dielectric material. So, this is how the dielectric has got an effect on the capacitance. Introducing the dielectric between the two plates will increase the capacitance of a capacitor. We can take the other case now. When potential remains the same, that means connected to a battery. How do we maintain the potential same? We take the same capacitor we take and it acquires the charge Q naught and it is connected to the battery. It is connected here, see. So, we measure the voltage, this will be the voltage of the EMF source. So, all are in parallel, right, and now the potential cannot vary because the capacitor plates are tied to the constant potential source. Under this condition, when we introduce the dielectric, what will happen? Now also the capacitance will increase, but now not by reducing the potential, it is by acquiring more charge. How much it will acquire? K times Q naught. Originally it was Q naught, now it is K times Q naught, and thus the capacitance increases. So, what is the conclusion? Whether the charge remains constant or the potential remains constant or they vary, whatever it is, the capacitance increases because of introducing the dielectric material. It increases K times if the entire space area wise and the distance wise, if it is fully filled by the dielectric material. Have you understood the concept? So, in one single statement we can make it clear. By introducing the dielectric material in a capacitor, the capacitance increases. We have the next concept. See, this shows how the dielectric is introduced. This the two plates are taken and dielectric material is kept in between and it is rolled for the cylindrical type capacitor, and here you have a oil immersed capacitor, and how after it is rolled how it appears, all this. This gives us some understanding how the dielectric material is introduced in a capacitor. Now, we will see the force that is existing between the capacitor plates. There will be a strong force of attraction between the plates of the capacitor since the two plates have the opposite charges. Electric field due to one plate in between the plates is given by this expression. These are all known expressions to us. The electric field due to both the plates now in between the plates is given by this expression. Now, each plate will attract the other because they are oppositely charged by the force F. We are interested in finding what is this force. So, we try to use this expression, what is the electric field due to any one plate, and we will take there is one plate that is producing the electric field, one plate. In the presence of this plate we keep another plate. So, one is influencing the other. So, that kind of approach we will have here. When charge remains constant, what will happen? If sigma is the surface charge density of the plate, the electric field due to one plate is given by this expression. The force acting on the other plate, we know the force is Q times the electric field. So, we substitute for the electric field, and what is the sigma? We open it. Sigma is charge per unit area, right. So, we write it like this. This Q is also now brought to that one. So, it has become Q square, and the further modifications bring us of epsilon naught E square A, right. What is this E? This E is the electric field that is existing between the two plates. So, there are two fields we have to be little careful with. One electric field is the electric field produced by one plate, that is sigma by 2 epsilon naught, but the electric field existing between the plates is sigma by epsilon naught alone. So, this E here is representing the electric field that is existing between the plates. So, I would like to mark it here. This electric field is sigma by epsilon naught. This is the total field that is existing because of the two plates. So, what is the conclusion? The force is existing because of the electric field that is existing between the plates. Now, we go ahead to find out the potential when it is remaining constant. When the plates are connected across the battery, the electric field is given by this expression. So, in that case also we try to write in terms of this. So, thus the force between the two plates can be found knowing sigma, E, V and D and A for the capacitor. Whatever be the case, there is a force existing between the two plates. When there is a force, there is energy related to it. So, we will try to find an expression for the energy. All that we will be able to do in the following lectures. So, when the two plates are kept, there is a force existing between them. If we do not keep them separated, what will happen? The two plates will come in contact and the charges are likely to get nullified. What will happen when the two forces are existing? See, the two plates will come in contact, the charges get cancelled, one will cancel the other, the annihilation will happen. So, by introducing a dielectric material, we prevent them from coming in contact. When we place a dielectric material between the two capacitor plates, what happens? The dielectric material, which is a non-conducting material, prevents them from coming in contact. So, it has got a role to play. The dielectric material will increase the capacitor of the capacitor and also prevents the two plates from coming in contact. So, we have learnt about the force that is existing between the two plates also. Shall we summarize what all we have learnt in this lecture? In this session, we have seen dielectrics and types of dielectrics, the effect of dielectrics in capacitor when the charge remains constant and when the potential remains constant. Also, we have seen the force existing between the plates of capacitor when the charge remains constant and also when the potential remains constant. It is time for us to test our understanding by answering these questions. Explain the effect of dielectric material in a capacitor by taking the cases of charge remaining constant and potential remaining constant. Derive the expression for the force between the plates of capacitor for the cases of charge remaining constant and potential remaining constant. As there is a force existing between the plates, there is a possibility for energy also getting associated with the plates. That we will see in the upcoming lecture. Thank you for watching this program.